This video is going to go over polarity. So how can we look at the structure of a molecule and figure out if it is polar or nonpolar? So you guys already know how to do polarity looking at electronegativities. This is just another way to look at this. Then we're also going to go into a little bit more depth here than we did last time. So you guys saw this chart in your introduction, and we have the electronegativity differences. And we have a general just ball and stick model of some molecules here. So let's take a look at those and see what we notice about polarity. So our first one, if it is a 0.1 electronegativity difference, that is going to be a non-polar molecule. So this molecule 1 here is non-polar. Molecules 2 and 3 are going to be polar molecules because their electronegativity difference is larger. So the difference between polar and nonpolar, which you'll remember from earlier in this unit, polar has an unequal sharing of electrons. Nonpolar is an equal sharing of electrons. So polar is unequal. The electrons are going to spend more time around one of the elements than they will the others. And nonpolar is the electrons spend an equal amount of time around all of the elements. So how can we tell just by looking at this first molecule, just by its structure, that this is going to be a nonpolar molecule? And we can do that because all of the outer atoms are exactly the same. So we have this central atom here in the center, and then we have these orange atoms all around it. So all of these orange atoms are exactly the same. So because they're all the same, it is going to end up being a nonpolar. And that's because all of them, where they're the same, we get a little bit of symmetry in here. So we can have the same pull in every single direction. So it's sort of like an equal tug of war that's happening. And that's what allows this to be nonpolar, and that all of the electrons are spending equal time around everything. Now let's look at polarity though, in terms of a polar molecule. So looking at molecule number 2 here, we do have all outer atoms are the same, right? This looks like our rule should apply here, but there's something different happening on the central atom. On our central atom here, we have lone pairs. So if you have lone pairs, that is going to tell you that you have a polar molecule. So if you have lone pairs on the central atom, and even if the outer atoms are exactly the same, you have a polar molecule. Now, what if we have different atoms around the outer side of it? The outer atoms, if they're different, that is also going to be a polar molecule. So if not all the outer atoms are exactly the same, we have something that's polar. So this is a very quick way that you can just sketch out a Lewis structure and figure out, is something polar or nonpolar? So I want to go through a couple examples of this with you with our Lewis structures. So for our first example, we're going to talk about nonpolar, and it's SiBr4. So the first thing we want to do is jot down our Lewis structure. Silicon, of course, is going to be our central atom here, and it's going to be bonded to 4 bromines. And our bromine is all the same. These are all the same, so I'm going to write them all in one color. And we can't forget the lone pairs around bromine as well. So this one is going to be nonpolar because we have the same type of atom all the way around the central atom. So it's really easy then to see how this looks very similar to our example on that chart, where we have the same thing all around it. So this will be nonpolar. Let's look at a couple examples of polar though. So here's one example of polar, which is SF2. So SF2, there are multiple ways to draw this Lewis structure. I'm going to draw it at a 90-degree angle, which is not the correct Vesper theory, right? This is going to be a bent molecule. So here's our Lewis structure, and this is a bent molecule, and it almost looks symmetrical, right? If we were to have a dotted line here and chop it in half, we could see a little bit of symmetry, right? So it's not enough just to rely on symmetry if something is polar or nonpolar, because that can be very misleading about what's happening. So in this case, we're going to use our rule that we had before. So we have a central atom, and we do have the same outer atoms. However, we have something different happening on the central atom. We have 2 lone pairs. So anytime there is a lone pair on your central atom, even if it's just one lone pair, that is going to make it polar. So this one follows the rule here like molecule 2. So if there are lone pairs on the central atom, then you have something that is polar. Let's look at our last example. SiBr2s. So color coordinating, I'm going to use green for Si because that's going to be our central. I'll use orange for Br2, and then I will use purple for our S. Silicon is going to go in the center, and this is going to make a trigonal planar shape here. And so our trigonal planar shape looks somewhat like this. Now, of course, it would technically be correct as a Lewis structure to draw at 90-degree angles, but we're more concerned with polarity here than we are with our Lewis structures. And even if you drew this without the correct geometry and you had everything at right angles like this instead, while missing lone pairs, but anyways, even if you draw it like that, you can still get the gist of whether it's polar or non-polar. So this is going to follow the rule like we have set up in molecule number 3. So if outer atoms are not all the same, then we have something that is polar. And that's because we introduced some asymmetry here. Now, once again, the symmetry side of things gets a little bit funky because we could say, well, look, it's symmetry down here, right? And it looks symmetrical, but in three-dimensional space, it's not exactly the same of how that works. So it's good to know the other rules as well. So looking at this, we have some different outer atoms. And since we have different outer atoms, that is going to fall into the polar category as well. So this is still in the polar category, but I'm going to write it next to it here as well. So this is still polar. Okay, let's have you do some practice problems. So here are 3 quick practice problems. What I want you to do, I want you to jot down the Lewis structure real quick and then figure out, is it polar or non-polar? So you can pause the video and try all of these, and then we'll go over them in just a moment. Okay, let's go over these. So quickly, let's check our Lewis structures. For CH2O, we have a trigonal planar molecule here that has a double bond. SiF4, we have a tetrahedral molecule here. Those lone pairs are not clear. Let me clear those up. And then pH3, we have a trigonal pyramidal model here as well. If you drew your Lewis structures at a right angle instead, that is perfectly fine. So if you had something more like this, that is okay too. Totally fine. I just wanted to draw some correct geometry in there as well. Okay, let's go over if these are polar or non-polar. For CH2O, we have different atoms going on the outside. Whenever we have different atoms here, this tells us we have a polar molecule. So just like in our chart up here, molecule number 3, that would be our example to follow. Let's keep going. Number 2, we have our central atom, and then we have all of the same on the outside, which makes this one non-polar. So this would be like molecule 1 in that chart. So everything is the same on the outside. Now pH3, all of our hydrogens are the same. However, we have a lone pair, and that would be like molecule number 2. And this is polar. So if we have that lone pair, that overrides everything being the same on the outside. Okay, so hopefully you're feeling really good about being able to look at the Lewis structure and see if it is polar or non-polar. Real quick, I want to introduce you to a concept called dipoles and partial positive and partial negative charges. So this first image here, which is a little bit pixelated and grainy, so I apologize. But let's say we had this compound here, and we want to look at where electrons are spending most of their time. So, and there's just 2 here. So we notice that there's more gray around this oxygen than there is around hydrogen, and that would be the electron density map. So that being said, if electrons spend more time around a certain area, they bring that negative charge with them. We're getting all of these negatives around it. So that means we have a partial negative charge. So this symbol right here is a lowercase Greek delta, and it stands for a partial charge. And we're going to draw this off to the side on another molecule. And we're going to draw this in H2O. So H2O looks like this. And let's put some colors around it. So it looks like that. So if we are looking at H2O, H2O is going to be a polar molecule because while the H's are the same, we have lone pairs here on our oxygens. This is a polar molecule. So when we have a polar molecule, the electrons spend more time around one area than another. And that area where they spend more time around, we can figure out because of electronegativity. So if we were looking at the periodic table, the electronegativity trend goes up this direction, pointing towards fluorine. So oxygen is up in this area, hydrogen's way over here. So oxygen's going to be a lot more electronegative. So what we see happening then is we make a partial negative charge by this oxygen. It's more electronegative. The electrons want to be around it more frequently than they do hydrogen, so we get a partial negative charge there. And if that is partially negative, then this side has to be partially positive. So these charges are partially negative and partially positive. So these are our partial charges. And all this is showing us is where the electrons spend more time. So when I'm looking at this, I can say, oh, the electrons are spending more time around oxygen than they are hydrogen. And this becomes really important when we get into something called intermolecular forces very soon, because when we induce a partial charge or a partial pole into these molecules, those poles are going to interact with each other. And remember, we are just saying partial because it's not a full pole. This is not an ionic compound. It's only a partial charge here. But let's say hypothetically then we had quite a few waters together. So if we have a lot of waters together now, something like this, remembering our O is red and our H is yellow here, then we're going to see some interactions happening. So we're not going to have just a single water molecule on its own. Normally we have like a glass of water. We've got a lot of water together. So when we have all of these partial positive and partial negative charges involved, we're going to see some interactions, because there's a good chance that this hydrogen here is going to be next to an oxygen over here. And this hydrogen has a positive charge and this oxygen is negative. And you guys know that like charges attract. So we're going to see some interesting things happening and some interactions here. And this is where we're about to head next in this unit, and looking at these interactions together. What happens when we have a bunch of polar molecules together? How do they interact together with that? Okay. Last thing to note with this too that has to do with our partial charges, they're called dipoles. So when we are inducing these poles, we might have what we call a dipole moment, which is one overarching charge of where our dipole is headed. So these small dipoles of our partial positive and partial negative charges, there might be an overall direction in our polar compound or polar molecule, all head in the same direction, and that is called a dipole moment. So whenever you have an overall polar compound and we have a pulling of electrons in one way, we call this a dipole moment. So the way that we drew this, I drew sort of a plus sign on the end where our positive charges were. And then I drew the arrow pointing towards the negative side. So down here at the bottom, we had the partial positive, and up here at the top, we were headed towards the negative side there. So that would be called a dipole moment. All right, so now you guys know how to just look at a molecule and tell is it polar or nonpolar based upon what you're seeing there. And then you guys know that electrons are pulled in a certain direction based upon their electronegativity, and that it induces a partial pole in that. We call overall that movement of electrons in one way a dipole moment.